right. Hey everyone, welcome. My name is Frank, and I lead the engineering team that built and runs what is now the Coinbase Derivatives Exchange. Today, we'll be talking about leveraging determinism, or, in more words, trusting deterministic execution to stabilize, scale, and simplify systems. This talk, I've got two things I'd like you to come away with. If you've got some mission-critical, important logic, right, make it deterministic. I'm gonna plead that you all do, but you all will be very happy you did. And if you've got deterministic logic, don't be afraid to actually replay it anywhere on your system for efficiency and profit. So, as a disclaimer, we'll largely be going over principles and practices directly from my experience, our experience running financial exchanges. We don't rigorously prove any of the concepts we're presenting here, and we're bringing any references to the canon or any prior art that we reference as inspiration, and it's all a case study. So, it's all n=1 here, and it's all anecdata, all right? So, all right, let's talk us and our problems. Quick show of hands, how many of you all are familiar with what an exchange does? Sweet, okay. That I won't have to go into it too much. Some of the nuances, right, is, again, we built and run what is now the Coinbase Derivatives Exchange. Formerly, we were a startup called FairX. We built a CFTC, read some government agency, licensed trading exchange for folks to trade financial contracts with each other. You can submit us an order, right, to buy or sell something for some price, and we'll let you and the market know asynchronously when you successfully trade and what price you get. Think of exchanges as financial infrastructure. Everyone who participates in finance relies on an exchange to provide the real price of things traded on our platform, and relies on us to fairly assign trades and values for folks who want to exchange stuff. First thing to think about for an exchange is mission-critical code, right? A bug on our system could result in catastrophic problems for not only ourselves, but generally customers, right? And all of the clients on our platform deposit millions of dollars of funds, millions of notional, because they trust an exchange to be correct, right? Potential losses we risk are multiple orders of magnitude more than any revenue we might make from a transaction. In a previous life, running like a Forex exchange, I think we'd be, our clients would trust us with orders for millions of dollars, and we'd maybe be happy to make 0.00001% on it, give or take a zero, right? So anyways, our business logic has to be rock solid. Exchanges absolutely have to be correct, right? Second thing about running a financial exchange is that many of our partners expect us to operate as close to instantaneously as possible, and also to be as consistent. Exchanges, if we're the ground that folks stand on for financial transactions, we've got to be predictable and fast. In general, right, you want to expect P99 latencies to stay under a millisecond, right? And that's, to us, handled it back to customers in under a millisecond at the worst cases. Finally, we've got to keep records for regulators, clients, debuggers like me to actually be able to find out what happened on the system up to maybe even 7 years in history, so that folks can figure out what went wrong and why they might have lost some money, or it's so funny, I have security updates required. Let's defer. That's great. So yeah, You might ask here, right, if risks are so high and correctness bugs are catastrophic and performance bugs get instantly noticed, right, how do we actually add features to the system in a reasonable manner? Well, we've got to make sure our core logic stays simple. In principle, right, you kind of want to minimize the number of arrows and boxes in your architecture diagram as much as possible, right? If you can remove something, remove it. If you can avoid a dependency, avoid it, right? What we don't want, right, is a bunch of services that can fail independently and partially when it comes to sort of a financial transaction, right? What we want is actually a very hardened kernel and something that is quite well tested. So in general, we want to make sure that all of our code lives really our mission critical code lives in a monolith. Other thing we want to avoid is concurrency. We want to avoid concurrency at all costs, right? In the last 10 to 20 years, multi-processor systems, right, have offered programs an interesting deal with the devil. Run stuff in parallel, you get some more throughput and performance, right? You just have to make sure that you don't have any race conditions, then your logic is correct for every possible interleaving, right, of every line of code in your concurrent system. And you run that code over again, you can't count on the same things happening because you've left things up to the OS scheduler, right? I claim that simplicity through deterministic execution can often get you even more performance and throughput than concurrent logic. Let's describe deterministic execution a little bit, right? Think of a program as a state machine, right? So you have program counter, right, pointing to which line of code it's executing at, and then the line of code modifying the system, right? I stole the next slide from a talk Martin Thompson gave about event log architectures. So thanks, Martin. New inputs come into the system that has some existing state and might create some new state. Also, inputs might come into a system and then you might get some output, right? So in practice, the terminology we like to use is input we think of as requests or API calls. When they impact state, they might change the state of the system. Inputs might also come into a system, and we might rename outputs to be events. So if you'll hear me say inputs and requests kind of interchangeably, and output and events interchangeably. Another one is command for input and events for output. Here's what you can do. Let's assume you've got ordered inputs, meaning that buy this, buy that, sell this, sell that. If you have a sequence log of inputs, you apply deterministic execution. The idea is that at the end of your ordered set of actions, you should get the same state and outputs. So again, in practice, right? If I sequence my requests, I apply determinism to save a few syllables, right? I'm going to get replicated state and events, right? So at this point, right, replicated state machines, hopefully that perks up the ears a bit. How many of you all have heard of raft? Yeah, show of hands. Oh, sweet. Okay, so about half. All right. So we'll take a quick little detour. We'll talk a little bit about the benefits of raft. So high availability is kind of the main reason why you might want to make use of consensus. Let's talk about what it looks like when you don't have consensus. If I have some service, right, and through maybe no fault of my own, the machine crashes or something like that, service is down, I'm getting paged, right, not particularly happy, right, with, say, raft consensus, right, I have a service, I handle some messages, I have to replicate them to a follower to make sure that the data is on multiple nodes of my system before handling it. And the benefit of that is that when I can now elect a new sort of main leader to handle, subsequent services from then, and I can sort of continue on and maybe just handle the hardware failure and try to start up a new system, right? So for there's a huge benefit if your system basically needs to be up all the time to running in some sort of a redundant manner. And when you have a deterministic system, you can replicate your state machine and actually just run multiple versions of them and be resistant to failure. You might ask if exchanges have to be really fast, right? What is the overhead of this message replication? It just so happens that there happens to be some open source technology out there that actually replicates a raft log through a very simple binary encoding that gives virtually zero overhead and allows us to basically respond to customer requests after reaching consensus in less than a millisecond easily. And on the cloud, I think we're in the hundreds, the mid hundreds of mics, or even lower. This is pretty great because traditionally in the past, exchanges have needed to make sure that data is on at least two machines, right? Because when a hard drive crashes or a system fails, you can't have a complete outage, right? Like the London Stock Exchange, the New York Stock Exchange, they cannot go down during business hours, right? So what they've traditionally done is some sort of a primary secondary model, right? Where I handle a message, I put it in a sequencer, I don't do anything with that message until I'm guaranteed I've replicated it to a secondary, and the secondary has Acme. But that basically was the standard in exchanges, the state of the art for quite some time. But it's not super rigorous, and for something that is the bedrock of systems, we lucked out in that, and a new open source technology came up for us to use. So, what do we get with determinism? Well, we get fast consensus, and how do we get fast consensus? We get to make use of single-threaded performance. So, when you basically handle a bunch of messages and you're able to pin that single thread onto a core, you'll get significantly better latency and throughput, honestly, than if you are passing data between threads on a concurrent system. I think in the past, Java and a lot of web servers kind of had built a system where you have sort of a pool of threads that you pass work to, and it seems super scalable. But realistically, the cost of all that context switching and the data copying and all of that, it is dominates the benefits you get from the parallelism. So run your stuff single-threaded. It's actually quite fast. The other thing that's nice about having a single-threaded system, and that's deterministic, is that testing is quite straightforward, right? When you have a concurrent system, you have to build test cases for all interleavings of all combinations of all the code running on all your parallel threads. So that's a cross product of test cases to get right, and is basically intractable, right? But if your system is completely single-threaded, your test cases read very much like stories. You can do sort of behavior-driven development, TDD, and stuff like that, and it just reads straight through, and it's quite nice. The other great thing about single-thread determinism is you have great tools for troubleshooting. Here, show you. Let's say I've got a service running in production, and some weird behavior starts happening on the system. It hasn't crashed yet, but weird behavior, possibly buggy, right? I'm getting paged or something, I see the monitoring, I'm not very happy, right? Maybe it's gotten into a pathological situation. What do I do, right? Well, let's say, I was running a deterministic system backed by a sequenced input request log. What I would do is when the weird stuff starts happening on my service, right? I'm gonna copy that entire request log to my laptop, I'm going to rerun that service on my laptop and literally run and the weird behavior is guaranteed to show up because the system is deterministic, right? As long as you make sure your business logic is deterministic, those business logic, pathological cases will show up. And so to figure out what went wrong, run it in a debugger, right? So that hopefully being able to view all the variables and everything will hopefully help me dispel the question. And I'm sort of kind of happy, but I still have this weird stuff in production that I've got to fix. But at least I figured out the root cause and well set up for any RCAs or anything like that. So yeah, deterministic stuff, operational benefits, performance, ease of test. Sign us up, right? So when we built an exchange from scratch about 3 years back, we decided to jump on this sort of latency open source fast raft cluster. So we built something kind of like this, right? Now there's 3 monoliths, which kind of sounds like an oxymoron, but all of our core logic, the stuff that matters, is in that, all right? So what you're seeing on the screen is kind of our 2 environments, right? We sort of are running the really latency sensitive stuff on bare metal with some basically API gateways, or you can even think of them as services that demultiplex stuff from clients and send them into our matching engine and our logic, right? And we also send out a bunch of events to the cloud for storage, right? And analysis and all the business intelligence stuff. This is your sort of pretty maybe standard hybrid cloud setup, right? So let's trace a message to our system. Let's say Alice wants to buy 2 nano Bitcoin contracts at 20,000. Alice will send a request to our gateway. That request comes into our raft cluster, which has all of our logic. We go ahead and acknowledge that request, send it out to the public and to Alice, right? This is done inside the Metal Data Center over like multicast UDP, so it's like pretty fast. And then finally, we also go ahead and send the event, right? And folks who sort of know about sort of a command sourced event streaming, right? This is the pattern, right? We'll send an event now to a replicator, and this replicator could be something like a Kafka or something like that. We use Aeron for our communication, but and then eventually, right, that event that Alice submitted an order will get written to the database. The order gets written to the database, and non-latency sensitive consumers or high throughput consumers will receive it later. So that's great. So blue arrows on the screen here are requests that come in, and red arrows are events that come out. The relative size of these arrows is important, and I'll talk about them very soon. So yeah, let's talk about what's actually in those requests. So Alice sends us a request to buy 2 nano Bitcoin contracts, 20,000, right? It's like 5 pieces of data, right? That's about 100 bytes maybe. And then let's say Alice successfully buys those 2 Bitcoin. If she trades with Bob and Charlie, right? She buys 1 Bitcoin from Bob and 1 Bitcoin from Charlie. What are the events that will actually get replicated over? Well, okay, so when Alice submits us an order, we tell Alice that her order was submitted. When Alice trades with Bob, we tell Alice that she bought 1 Bitcoin contract. We tell Bob he sold 1 Bitcoin contract. We told Alice she bought one from, well, we don't tell her she bought one from Charlie, but she bought another one, and we tell Charlie he sold another one. So one kind of request, right, 5 pieces of data, Alice buying something, resulted in like a mouthful of events that came out, all right? So we were a startup at this point, and we kind of ran it sort of more stable. We wanted to keep our burn rate low. What we were finding is that this is like quite expensive. The compute in AWS was like fairly reasonably priced, but this network egress and ingress, quite expensive. What do we do? Can we optimize it? Well, okay. What was the crux of the problem? business logic is pretty fast, but writing and reading data is kind of slow and expensive, right? In general, I think most folks' business logic is reasonably fast. The code you're writing, regardless of what it is fairly quick these days. But storage is a pain, and lots of round trips are a pain. Right? So having the fact that our system is deterministic help here, right? Well, here's a little piece. It's kind of I don't know if it was an offhand remark, but it was like, oh, here's one thing you could try, right? What if, when Alice submits us a request, we go ahead and send that request, right? Right now what happens is, you get a mouthful of events that come out and we burn a bunch of money on network, and we load the network and everything. How about instead of that, I don't send that. I actually just continue replicating the request. I just send those 5 bits of data, 100 bytes, over. And then I just replicate the requests all the way to my downstream services, right? Well, they'll say that doesn't work. Like, you need the service to turn the request into its effects, right? Like the database writer is not going to write the request because it doesn't include the context of whether it's been validated, what actually happened, right? So just something we do. If our system is deterministic, why don't we run another instance of our monolith on our downstream systems, right? And then send the really fat events over IPC, right? This kind of basically elides all that network cost, right? And so now I'm only replicating request. And so we go from something like this, where red is the big block of stuff, right? And blue is the little stuff. We're going from this to, right? Like lots of data, right? Like just a lot of data. We're going from this to the sort of kind of nice, just replicating the input request. So that's cool. Maybe let's try it. We hadn't heard of anyone really doing this other than I think like LMAX did it, I think a little bit ago. But we decided to try it. We were already in production at this time, so like making this like topology change was a little scary conceptually, but we were reasonably confident because of our good testing infrastructure. So we did end up deploying this change, and for whatever it's worth, we saved that, it was like 5x burst, like network cost, but like, more like 3x. Because in general, right, like, why does this work? And like you could theoretically do this on the other side too, right? Like if, let's say instead of us running in a bare metal data center, you could totally do this in the cloud, right? Like if your main writer logic is sitting in one region in the cloud, right? And then you have a lot of readers in other regions, right? You could replicate the raft log and then run little versions of your code to convert the input to output, right? So why does this actually work? Why is it cheaper? Why did it save us some money? One thing we realize is inputs are often smaller than outputs. And now this isn't always the case, right? But in general, right, like your input is contextualized by your existing business context, right? And then events come out, that's kind of what handling a request means, right? Like we have the business context. When you give us a request, we know what to do with it. And so we add some stuff onto the request, right? And then so the data that comes out should be, a union of our context plus your intention, right? So that's why inputs, we say are generally smaller. And here's the other thing. Inputs can be more consistent than outputs. The size of inputs can be more consistent than outputs. We always talk about 99 percentile latency, right? 99 percentile performance. But have you all considered what your 99 percentile network load is, right? So, okay, I've got a little thing, right? Let's imagine that Alice submits us a single request to sell 1,000 Bitcoin contracts at any price, whatever price. And let's say we've got a deep market. There's like 1,000 people willing to sell Bitcoin, right? What's gonna happen is just a ton of outgoing events, right? that small request comes in and is going to result in a ton of events. If we want to talk about this in database terms, right? Imagine if I go onto your Postgres database and I say, update big fat table set column 2, 3, and no where clause. You're just going to get a lot of wall entries, right? So I can predict what, so the input is actually quite small. It's like five pieces of data, right? About 100 bytes. And even my SQL request, maybe it's not that many bytes if you parse it down to the tokens or whatever. I don't actually know how it's stored internally, but like, it's probably not that much. But all the trade events that come out is possibly unbounded. We have no idea what the real behavior of the system might do, right? Depending on, we know based on the features we implemented. But, so input sizes and rates can be validated and rejected, right? Like if you submit me too much stuff, I'm gonna rate throttle you and not gonna let you fill up my input log with too much stuff, right? But events, they're kind of hard to validate and reject, right? You don't reject that something happened, right? Like I think that's a big thing in like the whole DDD like event streaming thing. Like how do you reject an event? You're just not happy it happened or whatever, right? And here's the other thing. Let's say you have systems, right, that read your events and then do more things in response to those events and put more events into your big, gigantic enterprise message bus / Kafka system or whatever, right? That if you have any sort of runaway positive feedback loop, that's how you get a thundering herd, right? What we can do here is we can maybe protect a little bit from thundering herd if you're only reading, if you put all your business logic, your key business logic in one place, and you're only reading from the inputs, then you avoid sort of crazy positive feedback loops, right? And you protect from thundering herd a little bit. And thundering herd is how you take down these gigantic auto-scale, cloud-scale, web-scale stuff, right? So, anyways, in summary for this sort of thing, right? If you replay your logs in production, right, by literally running more instances of your services and just replaying the ingress log in production to do things, you scale your system by decreasing the total utilization, probably maybe 2-3x. It's not that much, right? But the really nice thing is you stabilize it because you can now say, all right, I generally have a cap on how much input data I'm sending to the system. It's basically the summation of all of my rate throttles on all of my gateways, right? Does that makes sense? All of my API servers and all that. So you have a model, right? Whereas generally, nobody has any idea how many Kafka events are going to be streamed depending on some volatile situation that happens. And in markets, things get crazy real quick, right? So yeah, that's one reason to do this thing. Another reason to replicate compute, right? Because that's what this is, right? Like we replicate the ingress log, so that's data, right? But we're also basically replicating the compute using deterministic execution, right? We actually replicate that compute. It's a spectrum, right? There are trade-offs on either end, right? But, replicating compute can also simplify some downstream code. Now, deduplication is just an optimization, right? It's not architecture, right? Like, I think we're past dry, right? That's not architecture, but sometimes you wanna deduplicate, it helps. But it's still fun, right? All this is mostly optimization, right? It's a tool in your tool belt. So let's take a look at what that looks like. All right, we've got our system at this point with, I'm only replicating my input log everywhere, and it's extreme, right? To just kind of show the point, there's lots of ways you can move it from spectrum to spectrum. But all right, so let's handle GET requests, right? And it's purple because blue and red, right? Like we get a request and we have to send something back immediately, right? The whole point of it is it's like output basically, but it is also input. So a GET request goes into the raft monolith. Alice wants to know what our active order is. Hopefully this makes sense, right? We handle the request, we send it to our business logic, and our business logic, which owns the state, sends it back out. We can also fetch requests from other regions, and maybe through some sort of a private link, a cross connector, a VPC connector, whatever, we can handle that on our monolith and serve a GET request over there too, right? A query, basically. Well, that's kind of annoying, right? Like, I don't really want to be sending too much stuff over the, this could be the Great Plains, this could be an ocean between the AWS regions. So maybe I cache, right? I have some sort of a cache that, keeps queries, query data, right? And then I populate that cache by sending it output events, right? Because the cache, right, needs to know the state of the table, not the state of the request. So I have to send read events to a cache. It's effectively what you're doing is materializing the business context, right, into your cache, right, in your Redis cache or whatever. This makes sense, and maybe you could make the cache like a read through the first time and then cache it later times, stuff like that. What if we didn't want to do that? I literally have more blue things attached to these gateways already, right? The sort of obvious thing to do if I already have completely deterministic state down there is just request it from the instance of my state machine that's running locally. And therefore I can get all this data over IPC, right? Or even in process if you want to inject an instance of your main services library, right? So this is better, right? I'm no longer impacting the writer with my reads. In general, right, you want to separate reads from writes, right, in your system, and that's that's important for scaling. So yeah, now I can get rid of my cache, and I've got this great system, right? But what if at this point I'm adding a lot more services, right? A lot more services, a lot more features. They all have a bunch of different requests, like I could get active orders, I also want to get my balances or whatever. There's all these requests coming in. Do I want to run a little monolithy thing on each of them? Well, I don't have to if I put the cache back, but we already said we don't really want to send events to the cache, right? So instead, what do? Why don't we just run something that actually serves the data over inside the VPC? Because network traffic inside the VPC is actually quite cheap. It's not bad at all. That's literally how microservices work. They send messages inside the VPC to each other. So we can do that, right? We can replicate the request log from the main writer, the main raft monolith on the left, right? And we can send it to our read monolith, and then all of our gateways can go and fetch it from there. And this largely illustrates that the spectrum between replicating data and replicating compute, you can sort of adjust your sliders to whatever's necessary, right? And another benefit with deduplicating code here is that normally what ends up happening is if you're sort of writing your data to Redis, or you're maybe changing your database table to do something with change data capture, you're ultimately re-implementing your business logic again for read, right? And often it's maybe different teams that are re-implementing the core team's business logic, right? But what's nice about this is it's actually just this exact same code. So that same code just is used up and down the stack, and it's one implementation of logic. And that can be well tested, and it can sort of move in lockstep, right? And so that's how you get deduplication. Cool. Sounds good, right? Let's talk about, it's kind of a weird way to run things, so there's certainly a lot of considerations that you have to apply here. So here's a listicle. You have to make sure that this core code, right, your core logic, is very well tested, because otherwise, everything about the code will replicate, right? So again, this applies for financial stuff because it really matters. The harm you might create is possibly greater than the value you're providing to your employer, right? So if you have a bit of code that is incredibly well tested, this is a good sort of strategy. here's the other crazy thing. It has to be deterministic, right? What does that mean in the face of software changes, right? Like I add new features, or I change the behavior, or I fix a bug. What it means is that when there is a bug, your bug fix needs to be gated on a feature flag, because all of your downstream systems are eventually consistent, right? Because they're replicating that request log, but they're replicating it at their own speed. And okay, this is unlikely to happen, but like possibly you could have a bug on Thursday on the left side, the main monolith. You fix it on Friday, but it's possible that some of your downstream systems that have upgraded to the new code are still replaying logs from Thursday. You can't have it change behavior, right? You can't rewrite history. No, don't do that. That literally, it's like, that's why replicating data is a lot of times a lot easier, right? Because TCP won't just change its behavior on you when you change data maybe. But so all old behavior has to be respected when replaying it. You've got to enable new behavior with a proper request, a state change request into your writer to enable new behavior. And so what this actually does is it actually decouples the changing of behavior with deploy. Deploy should not change your behavior at all. You can actually run continuous checksums on the behavior of your system, right? And changing the code should not change that checksum until you submit a request to change it, but then once that request to change it gets replicated, all subsequent requests will have that new behavior, right? So it effectively, again, decouples behavior change with code deploy. Oh, randomness. We all need random stuff, right? Randomness is super useful in systems. So make sure to use a C so that you can get deterministic pseudorandom stuff. Another issue is that when you're single-threaded, while you're handling one message, it's blocking all the requests before it, right? So a tactic you can apply is you divide large chunks of work into stages, right? And pass it back into your request log to do the next thing. I'm sure some of you will realize that this is basically adding concurrency, right, to the system a little bit. So I don't know, your code is generally pretty fast, unless you're like iterating through a bunch of stuff. Probably don't need to do this, but if you have something that would cause your system to be unavailable because it's too busy handling a big request, consider it. For our raft cluster, and most should all fit in memory, right? So this is something that sounds kind of scary, right? It's like, oh, how is all of my data that serves my customers going to fit in memory? How is all the mission critical stuff going to fit in memory? Well, in general, right, we use a lot of kind of fluffy stuff. We use a lot of variable length fields. We kind of use stuff where we don't know what the size will be. The size of the limit of a size on a string is, I guess, the limit to which it crashes your program, right? So there's implicit limits on everything, right? So, but the alternative is if you use fixed length data for your mission critical code, generally dealing with numbers and stuff, right? All the static kind of create, read, update, delete stuff, right, can go live on a database somewhere. But if you have some stuff that matters, is generally numeric, or it's probably numeric, and maybe there are UIDs in there somewhere, right? That all fits. You can fit like a lot of customers' data in memory if you eschew variable length stuff and eschew arrays in requests, right? It also simplifies your programming model a lot. Sort of a corollary, right? Like, generally these systems run really fast. A lot of the most important financial systems in the world basically have their critical path run on one box, one thread. You can go up to millions a second easy. So But of course, you got to keep your 99s and 99.9s, right? Because those cases block everything else, so the harm of those is increased, right? So you want to apply some craft when building out your mission critical state. Finally, you got to protect that mission critical code from chatty clients. You have to rate limit on the outside, right? You don't want sort of bad behavior to basically denial. It's like you don't even need to DDoS. It's just like one chatty client will denial of service your system, right? So have sensible rate limits in place, circuit breakers, make sure you don't end up in weird feedback loops. But yeah, so all together now. What we like to say is that simplicity, right? It gets you stability, performance, and development speed. I'm sure you all have heard about the benefits of simplicity. Mentors and everybody have said, keep it simple. So I'm not trying to sell simplicity. Hopefully, trying to make the case here that deterministic execution gives you simplicity and gives you a bunch of these things. So again, if you've got some important logic, right, make it deterministic. And if you have it, yeah, don't be afraid to trust it and use it everywhere. It's pretty awesome. And if you already do this, I want to hear from you. Thanks, everyone, and I'll answer questions.
Okay. Thanks, Frank. So, any questions from the audience? There's one over here, and there's a couple here. We'll go here first. Ed, just shout out. There will be a microphone coming.
Oh, me first?
Just Jackson here, then.
All right.
Yeah.
Yes, thanks. Sorry, maybe it's a detail, but maybe it's how, when you duplicate business logic, you can ensure that if one application instance is down, everything still works. You have multiple monoliths, you call them?
Yes, they're running the same data, same logic. It's in a raft cluster.
It's the same code, in fact?
It's the same code and the same data.
All right.
Yeah, so the question was, right, like, when one of these monoliths die, right, like something attached to one of my downstream systems or one of the nodes of my raft cluster that's being used for consensus, when it goes down, how do we verify that things are going? The idea is that through deterministic execution, right, all of those blue boxes have exactly the same state or eventually consistent same state due to just replication lag, right? And so you can spin up a new one and have it replay the log and get exactly the same state.
It was floating around the middle there first, and then here. So.
Thank you. You quickly mentioned random seeds to get your determinism, basically. I was wondering, in your architecture, how you're dealing with time, basically, what is expiring, for example.
Yeah, great, excellent question. One timer with Raft, use the strong leaders timer. So basically, all of those blue boxes' view of time is stamped in the request log. Basically, when a request comes in, the Raft algorithm puts a timestamp on it, and that is the time. And so, of course, you may have, there are some complications when it comes to maybe there's clock skew on leader election or whatever, but this sort of standard kind of Raft operational best practices will help with that, but one call. And yeah.
Thanks, Frank. Absolutely mind-blowing talk. It's just incredible, and so many of the ideas resonated. I love determinism, and wanted to ask you, can you go into more detail on upgrade strategies? Like we've seen it, but if you've got a bug in your logic, so you gate it on a flag, what else could you do as you're adding new features? Do you just add a V2 of the feature, and it's always additive, or how do you do like split version testing of your system as do you upgrade the whole, do you shut down the whole system and then bring it back up with a new version, or you do rolling restarts? It's kind of like two different philosophies around split version testing. Thanks.
Yeah. So this is an operations question. Just to summarize, you can correct me if I missed anything. How do we upgrade this system with regards to new behavior and new data getting added in? Should we shut down the whole system, or should we do some sort of a rolling deploy? A big reason why we chose to sort of build our exchange on Raft is because it enables the ability to do safer rolling deploys than what was standard in state-of-the-art in exchanges at the time. Because that whole primary, so before it was primary and secondary, right? So what you could do is you could bring down primary, upgrade primary, but now you have a secondary, and it's just one secondary. And if you have any problems, then you're pretty sad. The reason why this isn't actually a problem for most of the non-trivial exchanges out there is they aren't 24/7. They get to shut down. It makes life so much easier. An exchange that is properly 24/7 is kind of a beast because, your disruptions of basically more than a few seconds are going to adversely impact all of your customers. So with Raft, what we do with the main consensus cluster, right? So that's the 3 blue boxes you see over there, right? Or 5. We go from 3 to 5, that's the first thing we do. And then you do them in a rolling deploy, right? Where you start with the followers and then you kill off the leader last and spin up a new thing. And then one of the 4 followers will become the leader. That code that is running, right, is the behavior needs to be exactly the same. So how do we test that? Well, what we do is we actually, just in our CI/CD, we actually run the last week or whatever logs on prod on new code and take a snapshot of the memory state and checksum it with the old code. And it's gotta be the same, right? And if it's not, then it's like failing it's like a build, the build fails, basically. Yeah, hopefully that answers.
One here, I think we're going to try and get as many questions as
Hi.
here in the front. So.
Really interesting talk. Thanks so much. Especially I'm here.
I have no idea where you are. Sorry.
Especially love the idea of being able to replay a particular request. I'm just curious about whether you persist different state changes, different states to be able to retrieve them and replay them locally when there's a bug.
So what's nice is you can retrieve, replicate. Now, of course, a lot of this assumes you can actually replicate 2 files in a streaming manner well, right? And but what that means is you can actually download data. You don't have to go to the hot writer to download the data. You can download that data from the replicator just like every other production service does. So you don't require a state change on the leader to do anything. You can run your debugging while the leader is going. Hopefully that makes sense.
So a state 3 months ago, if you want to replay that.
Oh,
you replay.
store that in S3, pull it out, replay it.
Right. Okay.
Yeah.
One just here at the front. Do you have that? And then one at the back.
Hi, great talk. So you were talking a little bit about how you have to use like a feature flag if you have a bug fix or a new feature or something like that. I was just wondering, so when a new input comes in, do you have to do some kind of a tagging of that request or input with the feature flag version in case downstream nodes need to replay that? They might, if they're not up to date with the current version of the code, they might need to load it in place.
So your downstream systems do need to be, they need to be at least those blue boxes, right? The things that are transforming requests into events, that has to be in lockstep. And if there was a bug in your deployment where you missed one in your rolling deploy, right? My suggestion is if you receive a message that the version is newer than what you expected, you should crash immediately and just not do anything. Because we're using compute to replicate the data, right? So it's like your copy, the integrity of your copy is off. You don't need to tag requests with the feature flag associated with it because the request log is sequenced. So all messages before the flag is turned on have the old behavior, and all behavior after the flag has been turned on has the new behavior. And your downstream systems will replay that exact log. So when you turn it on the leader, eventually it'll just come out via like replication to your followers
So
and your
it'd
downstream.
be all daytime based then?
You can do it anytime, because you can do all this rolling, basically. And you can separate when you deploy code for when you turn on behavior. And you can always turn off behavior, it's just an operational thing, right? Like, turning on and off behavior is just a request to the system. It is not like some fancy admin thing.
Thank you.
We're going to try and get that last question, because I know you've been trying, so. I got the back, but we'll go quick.
I have a couple questions. One is, you mentioned that you snapshot state of the memory. So all these boxes, like monoliths, do they share those, when you bring a new one, it just goes to a sprint, downloads the previous snapshot and replaces from certain stage? So because they need to kind of share that.
Yeah, so
one is,
you can either snapshot yourself or replicate the snapshot through the replication stream or go to S3. There's lots of different ways to rehydrate, right? What we have done is we found out on EC2 that local SSD, you like lose it if the EC2 instance gets terminated. Like you don't get your data back, even though it's written to disk. So it's like just like slightly better RAM, I suppose. So like what that means is you kind of want it in some really durable storage, like S3. But yeah, these snapshots, you can disseminate them however you like.
I see. And you described kind of single log, so it looks like there is one partition, so you cannot really scale it out. Do you
Yes,
scale
this
out?
might be a controversial statement, but you should avoid sharding as long as possible. As long as so if you can fit, right? Like if you remove all your variable length data and you use fixed length stuff, you can store millions of customers or even 1 billion customer data safely in memory these days. So for mission critical and distributed transactions are also horrible, right? So sharding sharding anything that matters and they have to talk to each other and do a two-phase commit is terrible. Don't shard your mission critical code if you can avoid it, right? Yeah.
Thank you.
Yeah, I got triggered there. Sorry.
Tell us how you really feel. Well, thanks, Frank. This has been super insightful. A round of applause again for Frank. Hopefully we see you guys at 11:50 in Windsor. Elspeth Minty from RBC is speaking about FinOps. So hope to see you guys there. Thank you.